So I suppose we're gonna get started. Hi, my name is Robert. I'm working for the German Aerospace Center, and I would like to take the next 35 minutes to tell you a little bit about the work that we're doing in Berlin. When I talk about my work, it looks a lot like playing SimCity. Who of you guys actually played SimCity in the past? Okay, so it's not totally uncommon to play SimCity. So when you played this and you designed your city wrong and you got like too many people working here and too many people living here, you got a lot of traffic jam happening, right? And this leads to angry citizens, which somehow hampers the development of your own city. Okay, and why does this look like the work that we're doing at the German Aerospace Center every day? Well, we do research in real-world mobility. We are researchers, and we try to make it better for everybody, not to have angry citizens, right? Okay, and with traffic and mobility, there's two things that are very challenging. One is, it's very hard to get data. It's very hard to ask people, where do you go, when do you want to go to, where. It's very hard to gather this data. Number two is, it's very hard to repeat an experiment. So once you came up with a great traffic management idea, then you try to implement it, right? And you try to prove that it's working properly. Now try to convince people to move the same way they've been moving yesterday, the exactly same way, and tell them, yeah, afterwards tell me how much did your trip improve after all. It's very difficult to repeat traffic management experiments in the real world. Therefore, we at the German Aerospace Center, we decided to develop a simulator, which we call SUMO, Simulation of Urban Mobility. Yeah, it doesn't look as pretty as SimCity does, but it does its job. We started to develop this simulator in order to understand traffic patterns, mobility patterns in the year 2001. So it's a very mature technology with a goal to simulate an entire city like Berlin, or all the car movements in the city of Berlin in more than real time. This was a design goal, and we are still able to do this. And it's not only a scenario player, if you like, it's like more like a full tool suite containing a lot of helpers, scripts, and tools to really build your simulation. We've been open sourcing SUMO since the beginning. It's been a project run at SourceForge, and we've had about 40,000 downloads in the last year, which is actually not bad for such a niche product. And interestingly though, most of our users are coming from the United States. There are indeed some German users, but actually states are still dominating us, right? Okay, and if you want to start to build a traffic simulation, then I guess we can start right now. There's a web wizard. When you install a SUMO, we can go, I hope it's working, we can go to the current location that we are now at. Okay, yeah, Ludwigsburg, sounds about right. Okay. We want to, oops, I didn't select the area. We want to have a simulation for this part. We want to have some cars, some trucks, some buses. We want to have pedestrians. I click on the generate button. Now it's downloading the live data for Ludwigsburg from OpenStreetMap. Now this is a perfect time to ask yourselves a very good question. Why does the German Aerospace Center does traffic? Well, besides aerospace, we also do traffic, research in traffic, research in energy. So it's like one of the other two branches of the German Aerospace Center after all. Okay, Still downloading map data. Maybe the area was too big or the wireless is too slow here. Anybody watching YouTube now? Oh, that's too bad. There we go. Now we got the stuff from OSM. Now we are converting this data live. We are adding cars, we are adding trucks, we're adding buses. And then it's starting to run SUMO. And it should be, oh, here it is. Here. Okay, so we have the trains running here. We're now somewhere here, I think here, right? Cool thing is now I can hit play. And we do indeed have cars moving. Okay. Cars are still moving a little bit funny, because those are basically all random trips, right? Random routes, random traffic, because there's no data source for real world traffic that we have right now. But you could start here. You could start with a basic simulation running in like 5 mouse clicks, right? Okay. So the drawbacks of the generated scenario are that you have limited network quality, something that we can only get from OSM, for instance. You can also get other data sources with high quality data, but OSM is for free. You have no information contained in here about the traffic lights. And this is a major factor that is hampering the efficiency of your network infrastructure. And we get only random traffic. We get no information where do people actually live and where do people actually go. So if you want to improve this, you basically need more information about the network, about your traffic lights, and about where do your people actually want to go, right? And this helps a lot. You can get this, but it takes some effort to gather all this data. We provide tools so you can feed in this data into your simulation scenario, but you still need to have access to kind of these data sources. Next question is, well, okay, I got an idea about SUMO. What can I run inside SUMO? What kind of vehicles can we actually simulate? Well, we usually say that it's almost every moving object. So cars, pedestrians, buses, trucks, trains, and even the traffic of goods, or container traffic is being able or could be simulated in a SUMO. Then we have a scenario to show you the city of Bologna. We need to make it a little bit slower. This is based on real world data. And here, do you actually see those red dots here? Those are you guys. Those are pedestrians moving. And some of these are actually here waiting for a bus. They are queuing up here, still waiting for the bus. Now they are getting in. The bus is still waiting because it's not on its timetable, and now it goes. We have even more people queuing up. Now they're getting in. If it's the right bus, if it's a proper bus line, right? You don't want to get in the wrong bus. And off we go. So you can absolutely simulate people living in the city. Sure, shoot.
If you say this is using real world data, does it mean that you bring real?
It's not live. It's not live. There's a data set from the city of Bologna. There was some elaborate questionnaire. Where do you usually go on Monday morning? How long is your a trip? There was some questionnaire for the citizens of this city to gather information about their mobility demand, and this was used as a data set to generate trips for this scenario.
So this sounds like really getting the data, setting it up, making it available,
It depends on the quality of the data, but yeah, it's usually like getting a basic simulation running, it's very quick. And then you can spend like from a person month to multiple person years to make the simulation behave very similar to the real world, but it's like an asymptotic curve, right? So you need to make sure how much quality or how much real world similarity do you actually need. It depends on your needs, right? Okay. One thing that we usually say is you don't need to have an only static or deterministic simulation. There's an interface with a variety of clients available where you can basically change or influence almost every aspect of your simulation. You can plug in all your traffic light algorithms, you can plug in how cars move, so you can basically, you have a way of influencing every aspect of the simulation while it is running. And this is a very good interface. We use it a lot for coupling simulators, for instance. The remaining part of my talk is merely about giving you an idea of what we are doing with SUMO, just to give you a broad range of application areas of what SUMO is currently being used for. First of all, we're using it for a driving simulation in Braunschweig, just to get a feel for how does a car behave, how does a human driver behave. And if you look within this chamber, then you have a lot of background traffic happening here. And in order to make this background traffic appear realistic, we use SUMO to basically generate this background traffic, and it is only displayed here in the viewer. Of course, with SUMO we look at autonomous vehicles and their effects on the road capacity and the road safety. So one of the basic questions was if we can picture or imagine having even more autonomous cars in the foreseeable futures. How does it influence the capacity of our roads? Does it increase or does it decrease? Does it increase a lot? Does it decrease a lot? Who here feels like autonomous cars would actually lead to an increase of capacity? Okay. Oh, very skeptical people here. Who feels like it's going to go to a decrease? The other part? Okay, okay, so some people don't know it yet. So what we did here, for instance, was we pictured we took a standard four-way crossing with actuated traffic lights, which are controlled by induction loops, so they try to prolong the green phase when they sense that there are more vehicles coming. Okay? And if we are looking at the capacity of this crossing, we can look at the length of the green time. If we have shorter green time, then this crossing is able to handle more vehicles within a shorter green time. The capacity grows, right? And we can also look at the delay of the vehicle that is induced by basically waiting at a red light. So if the green light phase time goes down, the capacity grows. If the delay goes down, the capacity grows as well. Simulation effects are here. We have several equipment rates, like what is the percentage of autonomous vehicles that we have on this crossing. Okay. And then we have the length of the green time and we have the length of the delay of the waiting time. And we have the morning hours, we have the peak rush hour time, and we have the after rush hour time. And what you can basically see here that we assume, or that taken from our simulation, we can assume to have the capacity growing once we got more autonomous vehicles. The idea is of course that with autonomous vehicles you can decrease the headway to your next vehicle. So you can put more vehicles on the same street segment, and you can coordinate the movement. So if the first vehicle sees green, then there's not a second reaction time before the next vehicle starts. They have them coordinated starting time, basically. Okay. Then we look at emissions. What are the effects of banning diesel cars from city centers? How does this affect the emissions for the entire city quarter, basically? And here SUMO contains an emissions model based on FEM, which is an emissions model for a set of vehicles that was developed by the Technical University in Graz, Austria. And so you have basically the ability to use SUMO to calculate emissions for the entire fleet, for your entire city, or for individual vehicles. We even have some parts of submicroscopic simulations, like detailed engine models. There's a plugin called Plexi, and this helps us with it. And yeah, just to showcase it a little bit, we designed a scenario which is a race between three cars. Who is actually able to foresee which is going to be the fastest car? Some people are going to picture the Alpha. Okay, so everybody's going to be for the Audi. Okay, sure. Okay, then we should check it. Oops. Oh, here it is. One engine. Okay, so we have cars here. This is a Bugatti. This is the Audi. And this is Alpha, right? So we kick it off here. And now we see them moving. I can go on longer, but it doesn't help, right? The Bugatti is actually faster by a lot. And if you look here, the simulation is able to simulate the engine power, the gear ratios, the aerodynamics, and the mass of those vehicles. And there are some further parameters which could be taken account in order to model or simulate those cars very precisely. Okay, so this is also one direction where you could be going to have very realistic cars in your simulation. Of course, optimizing traffic management or improving traffic management means looking at the traffic lights. And here you basically have the same situation 4 times over. You have a 4-way crossing with a standard fixed time traffic light. It doesn't adapt at all. Then you have another one here where you have induction loops. So you could basically prolong your green phase if you sense that there is more traffic coming. And then you have 2 advanced algorithms, while the bottom right is actually the most advanced, where you use car-to-car communication so that cars who are approaching the crossing are actually telling the traffic light that they are coming. And the traffic light is telling the car back that, oh, slow down a little bit. If you go 35 miles, then you're perfect. It's something that we call advanced green light optimized speed advisory. Okay? And if you compare these with the same junction with the same traffic, here we go. In all 4 crossings, you have the same traffic demand. The only difference in these scenarios is the way the traffic light acts, or the way the green light is being distributed to these 4 ways. And what you can see here is what you have today, basically, that you have some traffic jam going on during a red light phase. And at the bottom here, which is the future, basically, then you can see that you're almost able to go through your crossing without stopping. Yeah, shoot.
On the right side, you said the cars slow down, so they don't have to stop at the
Here.
red light, but is this also a sort of delay because it doesn't matter if you stop at the light or just drive slower?
Yeah, it is a form of delay, but the human factor for the driver, it's way better. It's way better for you if you're at least rolling compared to you're actually stopping. And with regard to emissions, it's also better to have like some coasting going on instead of like a full stop and then a full restart.
Does it help with actual capacity or not? Throughput? How fast they
Yeah. Yeah. You can actually prove that our GLOSA or the advanced green light optimized speeds advisory method yields the best throughput. It's even better compared to a roundabout. Okay. Yeah.
Did you also comparisons between having traffic lights compared to having roundabouts instead?
Yeah, roundabouts are good for traffic with a medium demand. Roundabouts are becoming less and less efficient if you have very strong demand, because usually there's a dominant traffic direction evaluating over or developing over time. Yeah, sure, but we haven't done this here because this was really focused on traffic light management algorithms, basically.
Also, one question. So you said in the bottom right scenario, you have car-to-car communication. Then I'm just asking myself.
It's not car-to-car. It's car to infrastructure, basically.
Okay. Infrastructure and vice versa, both directions.
Yeah. Yeah.
So for what do I delete all traffic lights if we assume all cars can talk to each other?
Because
we have tests for that, which even can prove that without traffic lights, it's even better because the cars are talking to each other.
there's still the possibility that you have two exactly equal cars coming at cross traffic, basically. And for this situation, you have to somehow, yeah.
There's an algorithm in the traffic light or in the car.
When you looked closely even here, where there were situations where cars had to come to a full stop. There was only a brief full stop, but there are actually situations where you still have to like stop cars.
Yeah, I still get it. I want to say, I would not be the mayor of that town. Should I invest now 100,000 euros for traffic lights? Although I know the cars can talk to each other, you can say, now stop, now it's my turn.
If we are talking about a whole perfect world, then everybody, every morning, would say, okay, today, like this morning, I want to go from here to there. And then there's a huge database building, there's a huge optimization algorithm running, and they would say, okay, Robert, you need to start at 8:05, and if you do that, then you have a green wave all along. If you can do this, perfect, then you wouldn't actually need this. But it's, once again, it's very hard to get data from the people about their mobility demand. But if you could, it's perfect. It's one way to actually say autonomous cars are perfect because we could finally influence their routes, right? We could finally say, okay, go here and take this route. Yeah, but I'm not sure whether people actually want this. Okay, we have another demo. Here there's car-to-car communication to traffic lights being used to reduce the travel times for ambulances. So once an ambulance wants to go through a traffic jam, it basically signals to the next crossing, okay, I want to go through quickly. And then this traffic light scheme basically gives priority to the green phases for this four-way, so this traffic jam could be, well, decreased. So the traffic, or so the ambulance could reach its target quicker, right? Another showcase when talking actually improves matters.
These scenarios are all based on the assumption that you have every car on your street, or not just every car, every moving object in your street communicating with the infrastructure, right?
This one is only the ambulance only talks to the next traffic lights. And the traffic light knows, okay, there's an ambulance coming this way, I need to give more priority to this part of the crossing.
So thinking with your four examples,
we will come.
Even if you have one or two or some cars that don't communicate, they
of course.
mess it all up. That's how I understand it.
You can have like you can design the simulation scenarios as you want. Basically, you can depict, or you can choose a certain percentage of cars who are equipped with communication stuff, and you can have other cars who are just plain old cars, and you can see how they interact with each other. SUMO is exactly the playground to offer you these capabilities. Car-to-car communication. So people are a lot talking about platooning, or having the, what's the German function name, Autobahnchauffeur, where you could basically have a platoon and a car merging in, and somehow you need to make sure that your platooning system works properly, and that there's stability in this control system. You can do this with SUMO as well. Here, we're gonna stop this one and this one. Okay, here you have the car wanting to join. And these cars actually use car-to-car communication and platooning plugins, where you can have your own platooning algorithm being added. And now it signals, okay, I want to move in here, so please make a space. And then see how these cars are actually moving backwards or being slower. And there's no central instance that is controlling this movement. It's all done via peer-to-peer, car-to-car communication messages. Okay, and now they're gonna have their proper distance again. And now we're done. Okay. People use it for this. Should?
But at the end, it really depends, or many of these simulations depend on how close they are to the reality or to the
Of course.
reality. So do we have some information about this? So how good is this? How good are these simulations?
We're talking to a lot of automotive OEMs with regard to using SUMO as a testing background or real-world testing background for control systems. So you can have very precise movements, but it doesn't. We would draw the line basically with, for instance, sensor models. So we don't have any radar information, or we don't model every little piece of the road that you would basically need to make sure that your radar or LiDAR would work properly. We couple with certain communication simulators, so you can have a very precise modeling of your communication protocols happening. But we're still looking at, let's say, traffic scenarios. How do bicyclists interfere with your control systems? So the idea is basically you can absolutely use SUMO to test your control units, but you should know what aspects of the real world SUMO is modeling.
I was more thinking on
That is perfect. You don't need, like in my point of view, you don't need any more detailed information for traffic light.
If you predict a certain speed in your simulations, how do you know that this really will become reality?
That's the tough part. This is exactly the tough part, because the next day in real life could be totally different to the day that you gathered your data from. It's some form of calibrating your data for macroscopic parameters like average throughput and car mix, like what kind of ratios are buses, what ratio are standard vehicles. Yeah, this is exactly the tougher part in researching mobility. Okay. Then we also have traffic prediction running with SUMO in Upper Austria. There's a website where you could basically have SUMO predict the traffic happening within the next 15 minutes or up to one hour. So SUMO can be also used for simulating the future. And last one, podcasts, future mobility concepts. We had a demonstrator for an exhibition in Rome where you could basically simulate the movement of podcars to transport people from the parking space to the exhibition entrance, all with a SUMO. Almost the last slide. SUMO is going to be, or SUMO is an Eclipse project since like four weeks ago, I think. And we are also building an OpenMobility working group to steer and influence the SUMO project and other projects that are basically coupling to SUMO. And if you want to know more, then absolutely go to the OpenMobility wiki. There is a mailing list there. We intend to kick off the OpenMobility the OpenMobility working group in the first quarter of next year. So if you feel like this is something that tackles your needs, then absolutely get in touch with me or the OpenMobility working group. Okay, then I'm done. Thank you very much. Please. Now it's time to rate and ask questions.
I've got a question. With lots of types of vehicles there, and then there seems an exception, which is ships and pedestrians who don't travel along a rail the way the others do. So a crowd of people can cross in a chaotic way.
Yeah.
Do you model pedestrians in that way?
We have
just travel from A to B.
There are two pedestrian models. One is a little bit simplistic for performance reasons, where you basically have pedestrians moving on straight lines. Basically, this is for performance reasons. But then there are also more sophisticated models. For instance, we coupled SUMO to the UPETSIM, to the pedestrian simulator from the Jülich, and they have social force models, and you could actually have a very elaborate pedestrian model being coupled to the SUMO simulation. So you could absolutely model crowds moving through a city.
Thank you.
Sure.
That was very interesting.
Thanks. Okay.